All right, in this lecture over worksheet 24, we're going to take a look at questions number 14 and number 19. You're going to do the rest of them for homework on another day, but let's get started. Number 14 says a block of wood which has a mass of 5 kilograms is at rest on a horizontal surface. A spring scale is attached to the end of the block. The spring scale is slowly pulled until the block just begins to move. At this point, the reading on the spring scale is 29 newtons. After the block starts sliding, the reading on the spring scale drops to 23 newtons. First question here is what is the magnitude of the normal force acting on this block? So we know that if we have a mass on a surface and we're pulling it with a spring scale, that if we do the free body diagram here, it looks something like this. Now, I know it's a little hard to see. I'll make those forces there purple. Maybe that'll help. All right. So by looking at this, we want to know what the normal force is. That's in the y direction. So we can go ahead and say sigma Fy equals MAY. And in the y direction, we'll just have the normal coordinate system. Normal coordinate system, which is positive y is up, negative y is down, positive x is right, and negative x is left. So we can go ahead and say that Fn minus Fg. I know I've been using lowercase n for force normal, and that's fine if you're doing that. That's what I almost did there a second ago, and either way is fine. The mass of the block, I think they tell us, is equal to 5 kilograms. But in the y direction, we're definitely not accelerating. The block isn't speeding up into the air or down into the surface, so that 5.00 kilograms is going to be multiplied by an acceleration of 0 meters per second squared. We do have equilibrium in the y direction, and we'll talk about equilibrium here in a second. But it pretty much means the acceleration is equal to 0. All right, so we get 0 over here. We get Fn minus Fg, and we can see that Fn is going to end up equaling Fg. And I'm not sure if I should be showing all my work there. The move there was just adding Fg to both sides, allowing me to cancel just like that. All right, so we can say Fn equals Fg. Let's see, maybe highlight it like that. And we're good, right? So we can go ahead and solve that. Just go a little bit further there. Obviously, Fg is mg. So Fn then is going to equal mg. And Fn is equal to the 5.00 kg times 9.81. And I think that's going to equal 49.05 newtons. Yeah. So there's our normal force there. And that is our answer to part A. Okay. Good. Let's see what part B asks about. Part B says, what is the magnitude of the frictional force on the block as it slides along the surface at a constant speed? Okay, so this is kind of particular. And it says, as the block slides at a constant speed. Now, they told us we had 2 scale readings. We had one right before the block begins to move, and that is 29 newtons. Let me get my highlighter. And then the other one was right as the block is moving at a constant speed, or as the block is sliding. And that is 23 newtons, so that is the lower one. And I want to say that's what they're asking for here. Let's look at the frictional force and how it relates to our free body diagram. we can see force friction is in the x direction. So if we sigma our forces in the x direction, and I know we're not specifying the force friction exactly, whether it's static or kinetic, but we'll do that in a second. What we can see is that I think we said pull is to the right, so that'll be positive x, and friction is to the left, so that's negative. So we're saying we have force pull minus force friction. And we have it equal to the mass, which is 5. That's a 5. 5.00 kilograms times the acceleration, which if the block is moving, right, and it says it is moving at a constant speed, I believe it says that. Yeah, I think in question B, it gives us that hint. It says, what is the magnitude of the frictional force on the block as it slides along the surface at a constant speed? Okay, so that's where they wait till right there in the question to say constant speed. We haven't dealt with accelerated motion yet, so but it still is a good idea to find the phrasing, because eventually we're going to open it up where it might be a constant speed, it might not be. So coming back down here then, we know the acceleration is going to be 0 because it's moving at a constant speed. Now you might say, well, what about when it just begins to move, right? So what we're kind of getting at here is that, let's go ahead and finish this first. So this is 0. And F pull is going to equal force friction. And once again, the move I made there, which I didn't show my work for, was to add force friction to both sides. And cancel here. What we're seeing there is it could be kinetic and it could be static, right? So what I'm trying to say is actually when it's moving at a constant speed, it's definitely kinetic, and the pulling force is equal to force friction. But this could have also been static, and so what I'm saying here is we have this idea of something called equilibrium, and so let's go ahead and define that right here. So equilibrium, there's 3 situations you're looking for, but equilibrium is when the acceleration is equal to 0. And whether we're working with static or kinetic equilibrium, we're in equilibrium. And so what I'm saying by that is the first case of equilibrium would be the object is resting. It's not moving. And that's what we mean by rest. Okay. The second situation is constant speed. We don't care which direction that velocity is pointing in. That's why we say constant speed. But that's another situation of equilibrium. And finally, the third one, which we haven't dealt with yet, is the object just begins to move. And you might say, well, if it just begins to move, it's accelerating. Yeah, it is going to accelerate right after it moves. But we're assuming when we say it just begins to move, that we are almost like freezing it right before it does move. That's like almost what we're doing. So we know that the pulling force is still equal to the frictional force. And that's how we're going to get our force friction. This is going to allow us to find force friction static max, right? because static friction can be smaller or larger to a point, right? But once it gets to the maximum, that's just as much static friction as there's going to be for that surface, or those two surfaces. All right, so three situations of equilibrium, and we have, if we had called this static or kinetic, it wouldn't have mattered. This relationship right here is going to be true in this problem for either. But what we're saying then is that the pulling force is different in those two situations. When the object is sliding, we see the scale reads 23 newtons. This is going to be our force friction then kinetic. And when the object is just beginning to move, this is going to be our force friction static, and it's going to be a max, right? And that's going to be 29 newtons. So I'm going to go ahead and write that down here. I think it's 23 and 29. So I'm going to go ahead and write it right here. So we're saying that force friction kinetic is 23 newtons, which is what the scale is reading, which is what the pulling force is when the object is sliding. And we're saying that force friction static max is equal to 29 newtons. And we should remember that force friction static max will always be larger than force friction kinetic. Okay, so I think we solved part B. I think this was, what is the frictional force when the object was moving at a constant velocity? And that would be 23 newtons. So let's go check that just to make sure. What was the magic frictional force of the block slides at a constant speed? So we can go back and check right here. This was question 14B. We're saying 23 newtons, 14B, and there you see it right there, 23 newtons. And I think we had 49 newtons for 14A. Yeah, 49.05. Okay, good. So good, or good so far. And so let's go ahead and look at part C. Now they want to know for part C and part D, what is the coefficient of static friction mu s, and what is the coefficient of kinetic friction mu k? So really the previous two problems kind of set us, or A and B kind of set us up for this. At least A did, and B we kind of expanded. So we found force friction static max and force friction kinetic. All right. So, all right. Let's go ahead and start then with static, mu static. And mu can change when it's static. So it can change all the way up to its maximum. So mu static can be smaller, which is kind of weird to think about, right? But it's true. So let's go ahead then and let's go ahead and solve for this. All right, so we're doing static max. Okay, so our formula we know about force friction is force friction static, and we'll just write, do we have to write max each time? We will this time, but usually I don't bother writing max every time. Force friction static max is equal to mu static max times force normal, right? This is our equation. Now obviously we rearrange this. We like to write it this way as mu static. I'm going to lose the maximum. Mu static equals force friction static. We know it's a maximum over force normal. And we can go ahead and solve for this. So we said friction static max was 29 newtons. And we said force normal, I think, was 49.05 newtons. And so if we solve for that, we can see that the mu static, God, now I want to write it again. Mu static max. I just can't make up my mind. All right, is equal to, what's that going to be? A little over 0.5, right? 0.6 maybe? All right. 0.59. Okay. Notice the units, right? Mu doesn't have any units. See those newtons canceling away? So that makes sense. All right. Let's go ahead and do the kinetic one for part D. So that's part C. We're going to write the same equation, right? Force friction kinetic equals mu K times Fn. Rearrange. Mu K equals force friction kinetic over normal force. Go ahead and plug in. I think we said force friction kinetic was 23 newtons. Put this over the 49.05. So this is going to be even smaller, which makes sense. Mu K should be smaller than mu static max. What is it equal to? Let me get my calculator going here. 0.4689, so 0.47. My eraser just came on. 0.47. Once again, no units because those newtons are just going to cancel away. All right, so let's go check. Let's check our answer for part C and part, whoops, some still in red. Part D, 0.59 and 0.47. Let's see what they say. 0.59 and 0.47. All right, there we go. We got it. All right, so let's go to problem number 19, which is going to be quite a bit tougher. But this one's like the lab, and I like this one. I almost assigned this one for homework, but I thought it'd be a good one to do because then I could talk about equilibrium and talk about the three situations where the object will be in equilibrium that show up, and so I thought that was good for that. Okay. Let's go ahead and go to number 19. All right, now number 19, it's going to be kind of tricky from the get-go with the free body diagram. So, and then the math's going to be a little tough. In the homework problem, you're actually going to do number 13 up here, which looks very similar in the free body diagram, but the math isn't nearly as hard. So I figured I'd do the tougher one, then assign for homework the easier one, which makes way more sense than the opposite, right? Teachers should do the tough ones and then let you practice the easier ones. I think that's oftentimes not always what happens, but I think that what should happen. All right. So, anyways, a sled with a mass of 45 kilograms sitting on an icy horizontal surface, which has a coefficient of kinetic friction of mu1 equal to 0.155. A rope is attached to the front end of the sled such that the angle between the rope and the horizontal alpha equals 28 degrees. And a force F is applied to the rope so as to pull the sled along the horizontal at a constant speed. All right, so then they say find the frictional force, find the normal force, find the magnitude of the force pulling. So it's pretty straightforward. They do tell us constant speed, right? We should be looking for that. That tells us equilibrium situation. What's tricky right off the get-go here is this force being on the front of the sled. We are not dealing with extended objects. We are dealing with a particle model, which means that all of our forces act from one point. So we're going to ignore the fact that it's on that the rope is attached to the front of the sled and just assume it's acting from the center of the object. Furthermore, this looks like two objects and it's actually going to be one. So even though it's a mass sitting on a sled, we're just assuming there's one object there to do this problem. If you want to try this problem, on your own, you can always pause it and then after you're done, see how you did. But this one, like I said, the math's a little trickier. All right, so let's go ahead and draw our free body diagram. So something like this. And I'm just going to go ahead and draw that rope there. And even though I know it's going to act from the center, where's the center? I don't know. I'm going to put the center right there. And let's go ahead and draw these forces here. So let's pick a color. Let's pick orange. right away we got a force gravity. We also have a force normal. I'm going to use lowercase n. We do have a frictional force. Pretty sure they said, yeah, they told us a mu1, right? And then we also have a pulling force from a rope. So we're going to go ahead and call that tension, but in this case, I think they just call it F, right? So instead of calling it T, which I would normally do, they went ahead and gave it the letter F. So I'm going to just call it F. And then we got the angle is alpha, and alpha is 28 degrees. Okay. So we're saying that we have this force F, which is going to be obviously parallel to the rope. And I think I went a little overboard with the length of that. Let me go a little smaller there. Maybe something like that. I'm not even sure if that's quite accurate. And that's going to be F. And we want to draw that alpha in, right? I think we should. So we're saying that there is an angle here of, let me see if I can color that. And we'll refer to it as alpha, and it's 28 degrees. Okay. I think I got that right. I want to make sure I don't mess that angle up. All right, and the mass is 45, and mu1 is 0.155. So mu1 equals 0.155. The mass of this crate is 45, or the sled plus crate is 45 kilograms. And this is also mu k, right? Since we know this sled is being pulled at a constant speed, so I can go ahead, if you want, it never hurts to just draw a velocity vector up there and remind yourself that it's constant. But obviously not part of the free body diagram. So 4 forces on our free body diagram here, and that's all we know right there. So I guess first thing is coordinate system. Are we working with the tilted axis? No, we only have one tilted force, so it'd be smarter to work with the normal axis system. So that's going to mean, whoops, let's go to black again. That's going to mean positive y is up, negative y is down. We'll call positive x right, and negative x is left. So we're going to have to split up, right, this f here into a f of x and an f of y. Okay. Giving us a right angle right there in red. And also letting us know that f then is a hypotenuse, fy is a opposite, and fx is an adjacent. Okay, so make sure you jot that in. And I think we're good. All right, so let's go ahead then and go back to the problem. I think the first thing they asked for is frictional force, if I remember correctly. What is the magnitude of force friction? Okay, so to get frictional force, right, which is an x force, we want to work in the x direction. But I just, let's go ahead and start there. So we're going to say, go ahead and write that down. And we'll write sigma fx equals max. We know that in the x direction we have two forces. It looks like fx and force friction. And fx is going to point right, so it'll be positive. And force friction, this is going to be kinetic, right, because it's moving. So we can go ahead and add that k there. I don't know why I didn't do it before, but that's okay. Is equal to the mass, which, what did they tell us that was? 45. All right. Now, it is moving at constant velocity or speed, so we know that this is 0. So we can go ahead and see where this is going, right? We'll add force, friction, kinetic to both sides. We end up getting Fx is equal to force, friction, kinetic. All right. So, okay. So far, so good. But that doesn't help us a ton, right? We don't know what Fx is. So this kind of puts us at a standstill here, right? And you might say, well, don't we know what force, friction, kinetic is? And I would argue yes. We do know a little bit more about force, friction, kinetic. We know that force, friction, kinetic. Let me get a little more room here. Is equal to mu kinetic times Fn. And we also know that mu kinetic, I think it was 0.155 for some reason. Is that what it was? Yeah, okay. Times Fn is equal to force, friction, kinetic. So I can sub that in, right? I can go up there and sub this in to here, right? I can do that. And if I do that, I end up seeing that Fx is equal to 0.155 times Fm. And I think a mistake students would make here is they would say Fn is mg. But you don't know that. And it's not. So it's wrong. So what do you want to do then, right? Well, we know Fn is a y force. So we can work in the y direction, but we're stuck. Right? I mean, I don't know what else to say. And this is why then when you go to the y direction, right? Okay. So let's go ahead and do that. I'm going to leave a little space. We'll probably come back to that and come down here. So in the y direction, what do we have going on here? We have how many y forces? And this is why you might want to do a redraw step, right? If you were to do the redraw step, I think you would see it really clearly that there's 3 and not 2. And I think a lot of times students would make a mistake and just say 2 y forces. So what you're seeing with the redraw step is you're seeing you got Fn, you got Fy, you got Fg. And then, of course, Fx and force, friction, kinetic. So what we're seeing here is that Fn is not equal to Fg. Well, what is Fn equal to? So let's go ahead and sum our forces. Oh, that sigma looks rough. I'm going to redraw that, and I wrote x. Okay. All right. So, okay. So, positive y forces, right? So we got Fn, and we got Fy. So we got to add those two. And then negative y forces, we have just Fg. Mass is 45. Acceleration is 0 in the y direction, right? Obviously. It's not going through the ground. It's not going up into the air and speeding up or slowing down in either direction. So we end up getting a 0 over here. We have Fn then plus Fy minus Fg. All right, so let's go ahead and solve for Fn because that's what we want. So we're going to have to, so what we're going to do here is we're going to add Fg. We are going to subtract Fy from both sides. All right, so if we do that, these cancel, and we're left with Fn equals Fg minus Fy. It's kind of hard to see. All right, Fg minus Fy. Go ahead and put maybe some highlighter around it, make it a little easier to see. All right, I think we can go a little further than that though too, because we do know Fg is mg, so Fn equals mg minus Fy. Fn is equal to, what was that mass? 45, yeah, okay. Just did a, I think the force of gravity is going to be about 440 or something. We don't know Fy, okay. Let me plug it in my calculator here. 45 times 9.81 is equal to 441.45 newtons minus Fy. All right, so that's a little bit better. All right, so we can sub that, right? Is that gonna help us? Is that gonna work? I think what I'm seeing here, and I just kind of want to show you. What's the best way to show you this? I think it's right now. I think what I'm seeing is this. I see one variable, two variables, three variables, right? This is already one of the ones we had. So we have three variables here. Fy, Fn, Fx. And Fn's on there again, but that don't matter. All right, so three different types of variables. We don't like that with two equations. So what we want to do is the same thing we did in that problem last lecture, right? Which is to rewrite Fy and Fx as in terms of their hypotenuse, in terms of f. So I think we said last time that that if I go down here, if I have a little room, cosine theta equals adjacent over the hip. And so we can say cosine of, I think it was 28 for some reason. Let me go look. Memory is not great here. Yeah, 28 degrees is alpha. So cosine of alpha, should have wrote that instead of theta, but oh well. Cosine 28 is equal to the adjacent, which is fx, over the hypotenuse, which is f. And if we solve here for fx, right, in terms of f, I'm just multiply both sides by f, we're seeing fx is equal to f cos 28. And by that same logic for sine, right, hopefully you can see all this and it's not getting cut off by the screen. There it goes. Okay, this is a little bit better. We have sine of 28 is equal to the opposite, which we said is Fy over the hypotenuse, which is f. Multiply here both sides by f. And by that same logic we just had a second ago, we see that Fy is equal to f sine 28. And this little step right here of, making sure we only have two unknowns is going to make the problem doable, because otherwise it's just I don't think there's a way to do the problem, right? So let's go ahead and rewrite up here. Okay, so we said fx is f cosine 28. oops, I'm using capital N for this problem. I don't want to change it now. Okay, so there's my first equation right there. I'll just write number 1. And my second equation then is right here. Oh, looks like I'm going in between uppercase and lowercase n. That's all right, whatever. You guys can handle it. And this is going to be f sine 28 degrees. All right, so this is doable now. We got these two equations. This is equation number 2 right here. And so how do we do this? Well, we just pick, we just sub, right? We sub into one, solve for something and sub into the other. So it looks like, what will be the easiest? Well, we did want to know, what did we want to know here? We wanted to know frictional force. I think that was, and to get frictional force, we wanted Fn. So we need to solve for Fn. So I think by solving this, then equation number 1 for F will be the best way forward. So we'll go ahead and make this, we'll divide both sides here by cos 28. Kick that over there. And we end up getting F equals 0.155 times the force normal divided by cos 28 degrees. Okay, so we'll then take this and sub that down here for, I don't know if you can see that. Take it all the way down there and sub it in for F. So, I'm gonna need another sheet of paper here. Let's see, let's add a page right there. And we'll rewrite this as Fn, try and keep this all on the screen, is equal to 441.45 newtons minus, what was that expression? 0.155 Fn over cos 28. Okay, I have that right. Times the times the sine 28. Okay, so that's kind of rough right there to work with, right? Definitely not easy. So let's go ahead and start simplifying. And I think once we do that, it'll get a lot easier. So let's start with this number in parentheses. So 0.155 divided by cos 28 is going to equal 0.1755. And I'm not going to round too much right now, because obviously we want to try and hold that rounding till the end, hold as long as we can, because then there's less error. So all right, so what is that? I think I lost something there too, didn't I? I lost my force normal. All right, let me rewrite that. Sorry about that. Let's get rid of that. I was going to say something didn't look right about that. There we go. Now let's multiply 0.1755 times sine 28. That's going to give us 0.0824. So we're saying minus 0.0824 Fn. Okay. And all right, this is kind of coming together, I think. So we have Fn equal to 441.45 newtons. All right, so what we're going to do is we're going to kick this over to the other side. Whoops. And we have to remember over here, this is really 1 times Fn, right? And we're going to add to it 0.0824 Fn. So we're going to get, these are going to cancel away. And we're going to get 1.0824 Fn equals 441.45 newtons. We're then going to divide both sides by that number. Told you the math was going to be a little intense. It's not that it's hard, but it's just tedious, right? And there's a lot of moves to make to get this force, because we just had to work through quite a few equations and make sure they were in the right in terms of the right number of variables. Let's go ahead and rewrite that then. Fn is equal, what is that equal to? 441.45 divided by the second answer. I'm getting about 5. Oh, whoops. All right, let me do that one more time. 441.45 divided by 1.0824. Okay, getting about 407.84, rounding a little bit there, newtons for my force normal. And I think this actually is the answer to part C. So it's funny, they asked for part B, right? But this happens quite a bit actually with these problem sets, where you end up to get one of them, you end up doing a little more, you end up solving out of order, right? Doing part C first. And that's quite all right. So 407.84, let's see, 19, yeah, that's our answer to part C. Okay, so we want to know the frictional force, so we'll go back up to the start of our problem. And we saw that Fx is equal to the frictional force, right? But we also from that, or actually from this expression right here, right? We see that friction is equal to 0.155 times Fn. So if we can just plug in for here, we can sub in, what was it, 407.84? Yeah. We'll sub in that 407.84 for Fn. Whoops. I was doing it here. It doesn't matter. Yeah, okay. I want to do it there. Okay. 407. Yeah, I should write it in a different color. 407.84 newtons. And so we're subbing that in, and if we multiply that, we see then that force friction kinetic is equal to that times 0.155, which is about 63.22. So when we multiply those two. All right, and that is our answer for part B. All right, right there. Okay, so far so good. All right, let's go back up to the problem now. Should we be checking those answers? Probably. But we could just wait till the end. What is the magnitude of the force F applied to the rope of the sled? So now we want to go back and get that force F, right? And this is in a combination of directions. So we could find Fx and Fy and use Pythagorean's theorem. But I think we could just do a little SOHCAHTOA and get it that way too. Let's see here. So if we go back... if we go back to the problem right here, we can see that if we know Fx, we should be able to use cosine formula to find f, right? Because f is the hypotenuse. And I think we know fx, right? Because I think we said fx is equal to force friction kinetic. So this 63.22 newtons is the same as fx. So this means fx is 63.22 newtons, right? And this is our adjacent. And so I think we can find the hypotenuse. Let's just do a little SOHCAHTOA. I think we can do it right off to the side. I hope you guys can see this. So we're saying that cosine theta, I think it might be alpha, but whatever, is equal to the adjacent over the hip. And that angle, I believe, was 28. Let's go check. Yeah, 28. And the adjacent is fx, and the hip is f. So we can plug in for fx. Probably move this around, right? Multiply both sides by f. Divide by cos 28. Cancel those. All right, so we end up getting f is equal to 63.22 divided by cos 28. Now, f is the hypotenuse, so it better be larger than 63.22. All right, let's go ahead and plug that in our calculator, making sure we're in degrees, not in radians. I'm getting 71.60. And units are newtons, of course. All right, so this is our answer to part D. All right, so let's see how we did. Part B was 63.22, and part C, which we actually solved for first, was 407.84. So let's go back and check. And then part D is 71.60. I guess let's go check them all. So it's question number 19. So we should have got 63.2, which I think we were pretty dang close, and we were right on the money with that one. 408 for part B, which we had 407, I think. And then 19, we had 71, or C, we had 71.6, which is correct. So same method, right? Work in the X direction, work in the Y direction, or even before that, free body diagram. Decide if it's a tilted axis problem, pick your coordinate system like we did. Split the oddball force up, F, into its components. Work in the X direction. I guess if there was like a side, something we did, little extra step here, was having to rely on this equation right here, which was kind of extra, right? Oh, highlighter's not looking so good. But yeah, but this equation right here, and I'm trying to highlight. Boom. All right. Having to rely on that equation too to get the problem done. But you can see we got stuck even using that second equation in the X direction. We got stuck right here, right? And then we had to work in the Y direction to get Fn. Fn is not always mg, which is what we saw in the Y direction. We saw that Fn actually is Fg minus Fy. And then we had the problem of Fy and Fx being too many variables, right? So we said we had two equations, right? But we wanted to get two equations with two variables, and we had one unknown, two unknowns, and then where did that go? God, there's so much highlight on here and so many things that I wrote down. Oh, I can see it. It's I had to pick a different color. And there's our third unknown, right? So, and Fn was on there twice. Yeah, okay. So we have 1, 2, and then 3, right? So 3 unknowns. We got it down to this equation, which only has Fn and F, and this equation number 1, which only has Fn and F. And we did that by using SOHCAHTOA, right? And rewriting Fx and Fy in terms of just F, and then sub and solve, right? And so we wrote an expression for just F and subbed it in down here. And when we did that, we had a mess of some math to do and ended up finding that Fn was 407.84. We then took that back up into this force friction equals mu Fn, and we could then plug in the 407.84, solve for force friction kinetic, 63.22 newtons. 407.44 was our, or 84 was our answer to part C. And then finally with force friction kinetic, that's the same as Fx. So Fx is 63.22. We then used cosine to find F. And that was what we did. So a lot of math, but the concepts, right? Don't get scared by the math, right? With the trees. You got to see the forest, which is free body diagram. Pick your coordinate axis system. Work in the x direction. Work in the y direction, and solve. And then if you understand those steps, then that is the big picture. That is the key idea to this unit. So focus on that. Regardless of these, this is kind of a one-off. There would never be one this tough on my tests. And yeah, because it's just the math is just too prevalent in this problem, right? We want to focus more on the physics. So but it's still a good problem and it's still fun to do. So there you go. That's it. Have a good day.